Thought about it, but then we're already behind. So we're further behind.
You get to choose what?
I get to choose, so I could just skip stuff. Yeah, I could definitely do that. All right, last bending example. Okay, then we're going to jump into shear. Okay, shear stresses and beams, which is going to be a function of our shear force in our beam, internal shear force, which would make sense. So in this case, we're working on the last part of the example where we were given the actual allowable bending stress in the wood and the steel, and we were tasked with figuring out what is the maximum uniform load as loaded there, as indicated here, right over the middle half of the beam, that we could put on this beam in order to make sure we didn't go beyond our allowable loads. So if we look at that, we could use our initial stress equation, right, bending stress equation, my over I. We rearrange that for the maximum moment because we know we now have a maximum stress that we can have in our materials. And then we have our moment of inertia that we calculated, right, based on the overall reference material, right? We transformed our steel into all wood, so now we have this moment of inertia for all wood cross-section. And then we have our Y based on that centroid, based on an all wood cross-section. And then in order to go to the steel now, we have to incorporate that change in stiffness, right? Because we transform the steel into wood, but in reality we have the steel plate. We want to know what the stress is in the steel plate, not this piece of wood that's imaginary, right? So we could essentially take our initial governing equations and then rearrange them using the information that we have to figure out what our maximum moment is. So if we look at the wood, our maximum moment that's allowed is 1200 psi times our moment of inertia, which is 2064 inches to the fourth, all over Y being 6 inches, right? Y would be our maximum distance. In this case, the centroid's at the center, so it would be the top or the bottom. And we get a maximum moment is 412,800 pound-inches. If we look at the steel, we get a maximum moment is our allowable stress, which they told us was 24,000 psi. Same moment of inertia, same Y, but now we need to multiply it by our modulus of elasticity ratio, right? Which was 16.67, which was 30,000 divided by 1,800. And we get a maximum moment, which will keep the steel from going beyond its allowable stress of 495,000 pound-inches. So obviously between the two, the smaller of the two controls, because as we ramp up applied loads, we're going to hit the small moment first, right? So we're essentially going to hit the limit of the wood. Yeah, Brendan?
And these max moments, can they be both in tension or compression?
Yes.
Okay.
Yeah, because our allowable stress is just given as a PSI, not a PSI with respect to tension or compression. So we're assuming it can handle the same in both directions. That was a good question. So, knowing that we have a limiting maximum moment at the beginning, right, I spent the time and actually derived our shear and moment diagram with respect to our applied loads. So now we know what the magnitude of this peak is. We could set that equal to 1.5 W6 squared. M max equals 1.5 W6 squared, or W equals M max divided by 1.5 times 6 squared. I don't know why I didn't just multiply it out as 36, but. So now we get W, 412,800 pound-inches. I want mine in pounds per foot. So I am going to use 1 foot per 12 inches. I'm going to divide that by 1.5 times 6 is in feet. Right, that was a distance along our beam in order to get our moment in our moment diagram. So based on this, one of the feet's cancel, so we just get pounds per foot, or 637 pounds per foot. Any questions? Essentially using our bending stress equation and then coming back to our shear moment diagrams to establish what is our limiting load, right? Applied load in order to get our limiting moment demand, okay? All right. We're gonna talk about shear, all right? Beam shear. Stresses in our beams due to shear. Well, in order to do that, so this is chapter 9 in the text. In order to do that, we're going to jump back to chapter 8, which is talking about normal stresses due to bending, and kind of determine where do these shear stresses come from, right? Where do these forces come from? Okay. And so first we're gonna go back to our little car lift beam scenario, right? 2-point loads, a tire load sitting on this beam. Okay, we've seen this one before. We have these shear and moment diagrams, right? Moment is P times A. A being the distance that these point loads are from the supports, if it's symmetrical. So we're going to look at what the internal forces are in a block, this little HHKK block that we've cut out before, right? So we're going to take a little slice of our beam and we're going to look at what internal forces are acting on it if we are in a position where we have constant moment, right? So this little sliver that we're going to take, delta x, is acting at this maximum moment, which is P over A, right? So draw a little box here. This box has coordinates because we're going to draw a free body diagram, right? This is H, and this is point K on our little sliver. If we were to cut that beam out, we would have an applied positive moment on either side of that section, right? And the magnitude of that, it's a strong whistler somewhere, P times A, right? And that's acting on both sides, right? If we are cutting our beam between B and C, our moment is constant, and if our moment is constant, then if we took out our sliver of beam, then the moment applied on each side of that sliver is going to be the same. Okay. So if we looked at our stresses, I'm going to come down here and we say we're going to look at, so this was right, free body diagram. And we've got moments that are applied to our free body diagram of our section. Now if we look at stresses and looked at a visual representation, right, free body diagram again, that same sliver, H to K. We have a rectangular beam, right? Our stresses are going to be linear. Our neutral axis is going to be at the center, right? This being our neutral axis, right? Place we have no stress. So as we look at the top here, due to applied positive moment on the ends of our cross-section, P times A, negative my over I. Our y is positive because we're going above our neutral axis. Our resultant is going to be a negative stress. Because our resultant's a negative stress, that means it's a compression. So the top half of our beam, if our moment is positive as it is, we're going to be in compression. And then below the neutral axis, our y becomes negative. Negative times a negative is a positive. Our resulting stress is going to be positive. That means that it's in tension. So those would be our stresses, our bending stresses, our bending normal stresses in our cross-section at point H to K. Right, looking at minus my over I. So that's the governing equation. Well, if we look at resultants, right? Stresses times an area are forces. So we really have these. Oops. Resultant forces acting at the centroid of this stress, which would be 2/3 up from the neutral axis because it's a linear. This is essentially a linearly distributed load, right, on the side of this cross section. So we're going to have a resultant force that's acting above the neutral axis and below the neutral axis, right? So if we take this cross section and now we cut it, we're going to cut it at the neutral axis. Okay. So we take our little free body diagram we made showing the stresses, the internal stresses in our cross section. Right? Those stresses, they act over an area, which means we have essentially a force acting above and below the neutral axis on each side of our cross section. And now I'm going to cut it at the neutral axis and look at what's going on the neutral axis surface. So if we go back here and we say, well, now we know that we've got tension stress acting. And that tension stress has a resultant force. Right? We're going to have a resultant tension force on the K surface and a resultant tension force on the H surface. And regardless how we cut this beam, it still has to maintain equilibrium, right? I mean, if the forces are not equal, this thing is going to be flying off into space. Well, right now, if we look at this cross section under constant moment, those two forces, Fk and Fh, are equal to one another. Right? And they're equal to each other because if we utilize the principle of normal stress, stress is force over an area. We can say the force acting on one of these areas, right, this stress area, is the stress on that area times the area. So FH equals the stress on H times the area of H. And the force acting at K is the stress at K times the area of K. Okay. And that gives us FK and FH. Well, the area of H equals the area of K because our member is prismatic. If we go to cut this beam along the length, it's going to be the same beam all the way, right? Because it's the same beam, then the area that this stress acts against is the same. We can also say that the stress at H is the stress at K. Because our moment's the same. Right? Because our moment's the same, it's prismatic. Moment of inertia is not going to change, right? So we look at our stress as my over I. The moment's not changing, and the geometry of the cross-section isn't changing, it's prismatic. So the area doesn't change, and our y over I doesn't change. So the stress doesn't change, so then we can make the determination that therefore, the forces on one surface equal the forces on the other surface, and that results in no force along the neutral axis. Okay. So the only force, if we drew a free body diagram of our beam in the middle of it, where we have constant moment, we're going to have no additional forces other than our normal forces. So that is looking at constant moment, okay? What happens when we have a changing moment? Well, if we have a changing moment, you can imagine these forces become different, right? The forces become different because the moment changes the stresses that are on each side of this cross-section. And what ends up happening is because you have different forces acting on each side of the cross-section, you're going to have to generate some sort of horizontal force within your member that's going to equilibrate the system. So you end up getting this horizontal shear force that's acting on that plane in order to equilibrate the inequality of the two forces acting on the two surfaces. So if we looked at a different little example to see some varying moment, right, a point load on a simply supported beam, right, PL over 4, maximum moment at the center. But if we wanted to cut out a section of this beam between B and C, right, at B and C we have this linearly changing moment, smaller at B than it is at C. So if we looked at a cross section, we would have a free body diagram that looked like this with applied moments, internal applied moments to this beam. You can ignore the fact that this shows two different materials. We're going to assume it's the same material. So we have our internal bending moments. Right. And we know bending stress now. Everyone knows my over I. If this beam is prismatic as it shows, we assume it's one material, even though it kind of shows two different materials here. But if it's one material, right, 150 millimeters tall, 120 millimeters wide, centroid is going to be at the center because of symmetry. So we're going to say that Y bar equals 75 millimeters. If that is the case, similar to our composite beam problem where we had the steel plate in the center of two, say, dimensional lumber, right? Two by 10s or whatever they were, okay? We have the centroid at the center. We have the moment of inertia of this cross section, which is just going to be a rectangle, right? BH cubed over 12, or 120 times 150 cubed over 12. That's 33.75 times 10 to the 6th millimeters to the 4th. Well, knowing what y is and I is, right, we could essentially determine that our maximum stress is at top and bottom of the beam. We're maximizing y. If we maximize y, we're going to maximize stress. So if we look at the bottom, for instance, our distance from the neutral axis to the bottom is essentially our centroid distance. It's negative because we're traveling below the neutral axis. We have a negative 75 millimeters. So if we look at B, we have y, we have I, we have our applied moment. We know that it's positive. We know that at B, our stress at B equals negative. M is 1.35 kilonewton meters. 1,000 newtons per kilonewton. 1,000 millimeters per meter. Times y is 75 millimeters. I decided to make everything into Newton millimeters. Divided by I, we decided is 33.75 times 10 to the 6th millimeters to the 4th. Everything cancels out here except for newtons per millimeter squared or megapascals. So we have sigma B, well that equals 3 megapascals. At C, if we do that same exercise, we get an increase in stress, which makes sense. Our cross-section is prismatic. We're not changing the shape of the cross-section. Area stays the same, right? Because the cross-section geometry doesn't change, our moment of inertia doesn't change. Geometry doesn't change, so our y max doesn't change. The only thing that's changing from one point in this beam to the next is the fact that the moment changes. In this case, the moment increases, so our stress increases. So we go from 3 megapascals at B to 4.5 megapascals at C. Well, that puts us in a world of hurt because now our cross section is not in equilibrium. All right, so if we remember from above, we have 33.75 times 10 to the 6th millimeters. We know that our normal stress, negative my over I. So we've got this cross section. And we essentially would develop the stresses as shown. Right? Where the stresses are 0, that's our neutral axis, right? So as we decided, our cross-section is symmetrical. Our centroid's at the center, so our y max to the top is our y max to the bottom. So our compressive stresses are going to be the same as our tensile stresses. They vary linearly, right? It's all a function of y, the distance from our neutral axis. So our stress distribution would show up something like this. So now we want to do what we did before, right? I'm going to cut our little sliver of beam at our neutral axis and look at the forces, right? Ensure we have equilibrium, so I'm going to cut this cross section, doing something like this, trying to make it look like a 3D element. We're essentially redrawing this diagram by cutting the top off. So we have this stress that we know is 4.5 megapascals at C and 3 megapascals at point B. Well, we're going to have a force that's associated with that stress. All right, this will be the force at C. This will be the force at B. We know that force is just the stress times the area. Going through the same derivation we did with a constant moment. So if we start by looking at the force, figuring out what the hell the force is at B, well, that's going to be our stress times the area. So we have 3 newtons per millimeter squared times our area. Well, we have 120 millimeters wide, right? And 75 millimeters tall. So the area that our tensile stress at point B acts is going to be 75 millimeters times 120 millimeters. Okay. Our stress is linear. It's a maximum at the base. It's 0 at the top. So we really have half, right? It's the area of the triangle. So it'd be 1/2 times that. So we get 13.5 kilonewtons. We have to divide by 1,000 to get that. We have 13.5 kilonewtons. If we go through that same process at point C, we get 4.5 newtons per millimeter squared times 75 times 120 times 1/2 divided by 1,000, and we get 20.25 kilonewtons. Excitement out there, huh? As mentioned, we always have to maintain equilibrium, right? When we cut out a cross section and we draw a free body diagram. If these do not equilibrate, this thing's going to be moving in space. And so in order to make sure that we know this beam's not moving in space, right? So we have a difference between FB and FC. FB does not equal FC. We must have equilibrium. Therefore, remember your math days, symbol for therefore, need additional internal force. Essentially, shear force required is required to maintain that equilibrium, okay? So our shear force, V, which is going to be now acting on this horizontal surface, is going to be utilized to maintain the equilibrium, to set it equal, to add to FB so that forces to the left equal to forces to the right. So that means that V is the force C minus the force at B, which is 20.25 minus 13.5, or we get 6.75 kilonewtons. Right? And we know from, that's probably a shitty color. Can you guys see that color? Okay. It is. It's not a good color. I mean, some of you probably like that color. I didn't mean to offend any of you out there. Okay? It's a beautiful color.
It's the color of your shirt.
I guess it is, isn't it? Not quite the same. This is a shitty color. This is a shitty shirt. All right. Just don't tell my wife that. All right. So we have a shear force. Well, we know from earlier chapters in the text, right? We have shear stress. Well, shear stress is, again, force over area. In this case, we use our shear force as the force, and then the area over which it acts. So we, in this case, have B over A, and we can figure out the shear force, right? 6,750 newtons, same as 6.75 kilonewtons. 120 millimeters, and if we cut this block and say it was 150 millimeters long, right? That's the length of the beam that we cut out. We would then multiply this by 150 millimeters, and we could get a stress 0.375 newtons per millimeter squared, right? This is megapascals. So we know the shear force, we can get the shear stress if we know the area over which it acts. Okay. Big takeaway here, right, is a moment that changes with x creates a shear force in the member. Right? Go back to, right, we have a changing moment. We have a changing moment, we have a shear force. Right? If we go back to our car lift, we have a changing moment, we have a shear force. We have a constant moment, we have no shear force. Well, we decided to cut the beam at the neutral axis, okay? And obviously this equilibrium needs to hold true at any depth. We could cut it at a quarter of the height, mid-height, which in this case is the neutral axis, 3/4 of the height, anywhere in between. Cut it in half at a horizontal axis. As you can imagine, the forces change in magnitude. If the forces change in magnitude, that means this shear force changes in magnitude. So you're going to get a variation in shear force over the depth of our member. Right? So if we go and we decide that we want to, I'm going to try a different color, maybe find one that's better. Well, definitely not going to draw that. I'm going to draw this. Straight line. So if we decide to cut, say, 10 millimeters, you guys see that color? Work okay? Okay. So we decide to cut this member now, not at the neutral axis, which was the mid depth, but we're going to just cut it 10 millimeters off the bottom. Obviously, that's not really to scale exactly, but close enough for what we're dealing with. So we cut it. sort of. Oh, I did not want to use that. Close enough. All right, so we cut it. When we cut it, we're going to have our same stresses. It's not what I want. What am I doing here? I don't want to draw it this way. I don't know what Tim was thinking when he was drawing these notes. But it's not what Tim today wants to do. All right, so I'm going to cut this beam 10 millimeters from the top. Broken record here, okay? Now I'm going to cut this beam and look at from the neutral axis down. So we're going to say that this is our neutral axis, and we have decided to cut 10 millimeters, right? So this distance here is 75 millimeters. And we know from before we're going to get this stress distribution that does something like that on that side. We're going to get a stress distribution that does something like that on this side. We had this 3 megapascals here. We had 4.5 megapascals on this side. We have some resultant forces, right? F at C, F at B, acting at the centroid of this stress distribution. Well, now if we look at cutting our beam at 10 millimeters from the bottom, our force now becomes, right, we'll call this say F sub 10. And F sub 10, right, the force associated with the stress that's below the 10 millimeter mark. Oops, I'm going to use blue. I'm going to say now our F sub 10 equals F sub B minus F sub 10 to 75, right? It's essentially all of the force that's above this line gives us what's left over. We get this 3 megapascals times 1/2 times 75 times 120. This is just stuff we've done before. Minus 3 megapascals times the ratio of 65 over 75. That essentially gets us to the magnitude at the line. Now that we have the magnitude, we multiply it by 1/2 times our area is now 65 instead of 75 because we're looking at all the area above. So now we get F sub 10, right? The force acting on that 10 millimeter sliver at the bottom is 3.36 kilonewtons. Not going to go through the rest of this, but if you did F sub 10, I guess we should call this F sub 10C, F sub 10B. Do that same thing for the force on the other side. You get 5.04 kilonewtons. Again, FB does not equal FC, right? The force on the left does not equal the force on the right. Therefore, we have a shear force that's acting along that cut plane That shear force is the difference in magnitude, or 5.04 minus 3.36, which is 1.68 kilonewtons. This magnitude is a lot smaller than it was at the neutral axis. Neutral axis was, versus, I think it was 6.75 kilonewtons at the neutral axis, right? So therefore, we can say that the shear force changes with all values of y. So as we move from one extremity of our beam to the other, the shear force is going to change. And it's going to be maximum at the center. Okay. And if you remember, when we looked at our stress blocks, okay, we looked at our stress blocks and we figured out that tau xy is tau yx because of equilibrium. So we just calculated what the shear force was on a horizontal plane in our cross section. Well, if you were to cut that beam right on the edge, we're also going to have a vertical shear at that same location in order to maintain equilibrium, right? So if we look at a rectangular section, this is the shear force behavior we're going to find, which we essentially found that based on the derivation we just did. And cutting our beam at a different section, finding what forces are acting on the normal surfaces, finding the differences between them, and figuring out what force is required to maintain equilibrium. That's essentially our shear force. If we divided that by the area, you would get a shear stress, and you would get a shear stress distribution, something like this. Obviously, it'd be 0 at the extremities. And when you get to 0, there's no imbalance of forces. If we decided to cut it, instead of at 10 millimeters, but 0 millimeters, we have no block to have force acting on it. If there's no force acting on our block, there's no way to have an imbalance in forces, and our shear stress, or shear force goes to 0. If shear force goes to 0, then our shear stress goes to 0. Okay. This is where you guys go to sleep. And I get excited. All right, we're going to talk about integrals for a little bit. All right. Because if me as an engineer, right, I know what the shear force is going to be at any given point, I could just cut it, right? But I want a nice, clean way of calculating what our shear stress is based on the shear force in our beam, right, and the geometry of our beam. So in order to do that, we're going to take some integrals to figure out what is the imbalance of forces at any given location in our member. All right. So again, if we look at a small section, if we looked at a sliver of a beam, and this happens to be our stress distribution, and we're assuming that we have a moment on one side, in this case it's positive, and as we move along the beam, we're going to have an increased moment on the other side of the member. Okay, so we have a varying moment in this beam. So if we looked at the moment diagram, it'd be linear or changing in some way. And we know because it's changing that our shear diagram is going to have a value to it as well, right? There's going to be shear at this cross section as well. So on one side of the beam, we're going to have a stress distribution that's going to meet our negative my over I equation. On the right-hand side of the beam, what changes? The cross section is not changing, but the moment changes. So our stress on the other side of the beam is going to be this new moment, which was our original moment plus a little extra, right? Maybe it goes up, maybe it goes down, but there's a delta in there, right? A change. And so we're going to have our original moment plus or minus whatever that changes, right? Whether the moment's going up or down. And we know that we're looking at some small length of beam, so it's a delta x, right? A small distance of beam. Okay? So we are going to look at cutting. Just love to cut shit around here. We're going to cut this beam horizontally at this ABCD, or ABED, sorry, ABED block. Similar to what we've done already, where we cut our section. In this case, though, we're going to look at what's going on with the section above. And if we look at what's going on in the section above, going back to what we just did, but now we're looking at integrals, so all we're doing is saying we're summing over the area, which would create our force, right? So the integral of my over I over the area is the force, right? Stress my over I, integrated over the area, essentially just adding up all of the stresses over this area gives us a force. So this is really, honestly, right, a force. So this is a force due to M, and this is force due to M plus delta M. Right? That's all that we're doing. And all that we were doing before is summing forces in the x direction. Right? We knew if there's an imbalance between the forces on one side of the block and the other side of the block, then we have to have a shear force. So if we look at that, looking at our three forces we've now established, right? We've got F sub m and F sub m plus delta m. Then we also potentially have this horizontal force F sub h. If we sum forces about the x, right, at our A, B, E, D block, and we know because of equilibrium it has to be equal to 0, we're going to say the integral A prime m over IZ times y dA prime, right, minus, so that's acting in the positive x direction, this force, F sub m. If we look at F sub m plus delta m, we essentially it's acting in the opposite direction, so it's going to be countering integral. Now it's m plus delta m over moment of inertia times y dA prime, the area over which it's acting. And then we have our horizontal force at the cut. We're going to cut it right there. Fortunate for us, got a couple things that cancel out. We essentially have the same force on both sides because on the right hand side we've got our original moment plus some delta. So that original moment force cancels on both sides, and it's really the delta, the change in moment, or the force associated with the change in moment, that gives us our horizontal force. So now we can say, from that, we could say F sub h equals the integral I bar, or A of the area, delta m over IZ y dA. Well, out of this equation, if we're integrating over the area, nothing changes with respect to the moment or the moment of inertia with respect to the area, right? Those are constants based on the cross section. You can say this is a constant. So we get delta m over the moment of inertia, integral of the area of y times dA. And because we're engineers and we do not like to do integrals, we give this a name and we actually calculate it without integrating. First moment of the area. This is Q. Right? Call this Q. Well, if we call this Q, our horizontal force is now delta M times Q over our moment of inertia. We're gonna stop there. Delta MQ over IZ. Try not to dream about that.